Hi, chemistry students. Let's talk about evaporation, and in doing so, we'll be able to move on to other properties of a liquid, such as vapor pressure and boiling. And we're going to try to do this from a physical understanding, which means we're going to look at how the molecules are behaving on an individual basis to describe all three of these characteristics of a liquid. So I want to start by just reminding you that each of the phases of matter that we apply to pure systems, pure materials, they tend to have a particular temperature and pressure in which they are the most stable. So when we look at a solid or a liquid or a gas or even a plasma, these particular phases will be more stable than others. So if we're for water, for example, liquid water at 25 degrees C and 1 atmosphere pressure, the liquid phase is the most stable. And we expect water to be in that phase. Same thing goes with the solid water. We know that that's going to be ice if it's below 0 degrees and 1 atmosphere. What happens if we change the pressure? What happens if we change the temperature? Those are going to change whether or not a particular phase is more stable than the other. So what we're going to look at, though, today is, in particular, what is going on when there's a spontaneous transition from the liquid to the gas phase when the liquid is supposed to be the most stable. Why does this happen? So we're going to get part of the story today, actually, because there's actually more to what goes on. So we start by, let's just choose a few molecules to concentrate on. So in this jar, I've got this liquid, whatever it is, some liquid, and I've chosen to look at three, one at the surface, one in the middle, one at the bottom. And we got to ask ourselves the question, this evaporation, what is it? Well, it's a liquid to gas transition. It's a vaporization, but not of all the molecules, of a few molecules at a time. So above the liquid is room for a gas. In the liquid, there's not much room for a gas, especially to be stable as a gas. So we can kind of rule out right away that some of the molecules can't evaporate. So we're kind of creating a condition, a set of criteria to evaporate. So let's do that. The first criterion we've just said is, to evaporate, I've got to be near the liquid to gas interface so that when I do leave, I can make the transition and become a free particle of gas. Pretty simple. So these other two, they're not going to be able to evaporate. So what else might be a condition to evaporate besides being at the interface? Well, if we think about these molecules, any of these molecules that are inside the container here that are liquid, they're held together with intermolecular forces. Those intermolecular forces have to be broken to become a gas, because in the gas phase, those intermolecular forces just kind of barely interact with the molecules, but they don't hold them close together. Therefore, we must have enough energy to break our intermolecular forces. And if we recall, we could look at a Maxwell-Boltzmann distribution and get an idea of what's going on here and what's going on in the container. If we have a container at a particular temperature, the Maxwell-Boltzmann distribution will represent the distribution of velocities. Not all the molecules are going fast, some are going slower. Actually, in this case, most are going slow. Slower than some arbitrary line I've drawn here. Let's imagine that this particular line is the line that represents the minimum velocity or the minimum energy to break the intermolecular forces. If that's the case, then only the molecules that are beyond and to the right of this line can break their intermolecular forces. And the area under the curve represents the probability of molecules having that much energy. As we can see here, there's a small fraction of the entire container that have enough energy, which would mean there'd be a small fraction of molecules at the surface that have enough energy to break the intermolecular forces. So if I'm at the surface, only a small portion of those molecules at the surface will meet the second criteria. Both criteria must be met to evaporate. So what would happen if I was to change the temperature then? If I change the temperature, maybe let's say I increase the temperature, then the solid line here represents the higher temperature and the lower temperature is represented by the dotted line. We have the same minimum energy to break our intermolecular forces as before. However, we see that at the higher temperature, there's a larger area under the curve, meaning there's a higher probability of molecules having this minimum energy. That means in the entire container, More molecules have enough energy to break the intermolecular forces. Therefore, more molecules at the surface will also have enough energy to break the intermolecular forces. And finally, that means more will evaporate. So now that we've talked about evaporation, we have an idea of what's going on there. I want you to consider this situation. What if we were to put a lid on the container? This lid is going to block any of the exiting gas that leaves, this vapor, and it's going to block it from leaving, and it's going to start to build up in the container. So here's one molecule that evaporates, and over time, a few more will evaporate. This will continue, but at some point we're going to see that some of the molecules will bounce around and actually hit the container, the liquid molecules below. The molecules above in the vapor phase, these bluish molecules, I've given them a color to kind of separate them, they are bouncing around off the walls and create a pressure. And this pressure is called the vapor pressure. However, at some point, the number of molecules that are evaporating and the number of molecules that are condensing will be equal. And at that point, we get an equilibrium. And what that really means is the number of particles that are free gas floating above, in between the lid and the liquid layer, that's going to be an equilibrium. We're going to have a same number of molecules in there, and therefore we're going to reach a constant vapor pressure. This vapor pressure is going to be determined by the temperature only. So it's only a function of temperature. If we change the temperature, if you think about it, we're going to change the evaporation rate, which we just saw. If we change the evaporation rate, we're going to have either more or less of these gas particles floating freely above. So the vapor pressure is dependent on the temperature. So if we were to increase the temperature, we would have an increased evaporation rate and we'd have more molecules evaporating. That means we'd have to have even more molecules freely above here to have two or more molecules that are condensing. We have to increase the number of molecules in the gas phase to increase the number of molecules that can actually condense. Therefore, if you increase the temperature, you will increase the vapor pressure. Vice versa, if you decrease the temperature, you should decrease the vapor pressure. Now let's get to this idea and this concept of boiling. We've all seen and heard and talked about it most of our lives, but we really have it kind of improperly put into our head of what's going on. It's caused by a certain set of conditions. And the boiling point, we have to remember this, the boiling point itself is a temperature. It's the temperature at which boiling occurs. But that's not what boiling is. Boiling is not a boiling point. Boiling is something different. It's specifically when the vapor pressure is equal to the pressure pushing down on the vapor. So in this case, we've got a lid and it's got some weight to it and it's pushing down via gravity, pulling down on it against all these molecules that are in this container. And if these molecules, if these little blue gas molecules can push on the container up at the same force that the lid is pushing down, then we've reached the point where we see boiling. This can happen not only as a lid, but it could happen if we remove the lid and we imagine what's actually going on inside like our containers when we are cooking food. The pressure down is caused by the atmosphere. So here we've got these air molecules. There's no such thing as air molecules, but you know what I'm talking about. We've got this atmosphere pushing down, and the gas particles here that we have coming out, the vapor, it has to be able to push this gas away. And for it to occur, the pressures just have to be equal. But that's not how we normally see it when we see boiling occur in our kitchen. Instead, what we see is something more like this. We see an energy source at the bottom. This energy source at the bottom of the container will get the molecules at the bottom of the container hotter than the molecules at the surface. So what happens is we can get these little temporary evaporations going on at the bottom that don't last. What happens is a bubble's created at the bottom. Here's this bubble, and it's filled with some of the molecules of the gas that have evaporated. So it's filled with some of these little evaporated molecules, and they start to push out on the molecules around them that are in the liquid phase. If the inside pressure can push just as hard as the molecules in the liquid are pushing. Then that bubble can float to the top and pop and come on out. At that point, we see the boiling that we normally experience in the kitchen. So boiling is quite interesting. It's the ability for the vapor pressure to push away whatever external pressure there is in the system. That external pressure could be the atmospheric pressure, in our case air, and we see these little bubbles that start to form during the boiling process because the heat source just happens to be at the bottom. So just recall that as the temperature increases, we notice that an evaporation rate will increase, and therefore our vapor pressure increases. As the external pressure outside increases, we would need a larger vapor pressure to boil. And therefore the temperature at which we would boil, because to increase the vapor pressure we have to increase the temperature, the boiling point would also increase. And finally, if we were to change our liquids to get a stronger intermolecular forces, then we would need more energy to break our intermolecular forces. That would mean if we had the same temperature, we'd have a lower evaporation rate because less of the molecules would have the ability to actually break the intermolecular forces. And we'd get a lower vapor pressure. And this means we'd have to increase the temperature even further to have a higher boiling point, or to have it boil. So we'd have a higher boiling point due to the increased intermolecular forces. Try to put this all together. Watch the video a few times, and I hope it helps you understand these properties of pure liquids.